Thanks, Alex. And yeah, I guess it's my prerogative to have a slot before you all escape. Seriously, I think we've heard over the last day and a half the sheer breadth and complexity and the challenge that's involved here. Each of you are bringing together lots of different partners and suppliers and thinking to try and work our way through to the best way of decarbonising and reducing pollutants from off-highway. So I wanted to share with you what we do in a bit more detail. Apart from organising conferences, what's the sort of breadth of activity, the type of activity that we do and we've done over the years, and which may in some way be able to help you in the future. So to that end, I wanted to talk about the sort of real-world performance measurement, emissions measurement of both regulated and unregulated pollutants that we conduct. We've now been going, as you probably know, for 13 years as a company, and although we're headquartered in the UK, I probably won't make a Brexit point, because Brexit is a very tedious and emotional topic, but an increasing amount of our work is elsewhere, not least in the US, in Germany, and increasingly in Asia and down in Australia as well. And our position in this is we are independent testing, independent real-world testing. That's what we like to do. We like to get our hands dirty. We like to get on to working with you on real applications in real situations. We also back that and sort of demonstrate what we can do by actually running tests ourselves, on vehicles, on machinery that we source ourselves and we test, and we actually populate databases which are then available to anyone in the marketplace. So if you're looking for benchmarking information, trend information, or even deep dives on individual pieces of machinery, often we will have tested that vehicle ourselves already, own that data, and can make that available. To the extent of we've now tested over 2,500 different vehicles and machines. Numerically, the greatest number there are cars and vans, but there's a growing number of off-road machines in there as well. So we're not just doing it for third parties, but we are backing that by doing it ourselves as well and making that data commercially available. And we work with everyone up and down the supply chains and researchers and the like. So so I guess the message from that is we're not just a simple test house. We are actually passionately interested in this area, and we build these bodies of knowledge and like to work with everyone. I mean, in specific terms, and what the bread and butter of what we do is many of the regulatory certification, surveillance type testing that is in Europe and is increasingly over here as well, extending that as well to things like retrofit accreditation. That tends to be schemes that come and go, that are government driven, that can be very intense for a period, and then finish, but we are able to deliver those sorts of accreditations, and we've done in a lot, for example, around bus retrofitting in the UK. We run standard PEMS equipment from both Sensors Inc. and Hariba, which meet all the sort of usual requirements and the standard pollutants, but also, and which will be a segue into the second half of my presentation, will be also currently unregulated pollutants and even species which would be in the category of sort of emerging substances of concern. So I'm going to take you through very quickly three areas. So construction, what we do in construction, what we do in marine, and then specifically looking at alternative fuels, and then I'll wrap up. So, we cut our teeth on the off-road testing, as I mentioned briefly at the beginning of yesterday, that there was a big construction project in London, which was at the time the largest construction project in Europe around redeveloping Battersea Power Station, which actually you can see there. If there are any Pink Floyd fans in the audience, which I hope there are, that is the building that's on the cover of the Animals album from 1977, and was a power station that was, which is in very central London, and was bucketing out noxious emissions right in the centre of London until it was finally decommissioned, and I think it was 1981. And it sat there derelict for a long time, very contaminated site and very difficult to regenerate, but extremely iconic. So you can imagine the planning and zoning agony that went through. But finally, about 10 years ago, they got through that, and it then became this very large construction project. So what we did, we worked with King's College and Imperial College in London, and we were able to get access to essentially pretty much all those machines on that construction site over about a 3-year period. So we were actually on that site, deep in big excavation holes, whether it was sunny, rainy, windy, whatever, because we had this one-off opportunity to be able to get our hands on all this equipment and test them in a sort of similar like-for-like way, doing their real work on this construction site. And if you look carefully, you'll be able to see the telltale hallmark of a PEMS unit in each of those pictures. So that's our PEMS units installed. So I put that up to give you, I guess, a sense of the sort of scale of what we're able to do, and the ability to go into pretty challenging locations and test on vehicles of all shapes and sizes. And from that, the body of data we built up, we were able then to, by owning all this data, then be able to do and understand, in this case here, the work-specific NOx emissions across those range of vehicles, segmented by the different regulatory stages from stage, in this case 3A through to stage 4. And we were able to see the reduction, so by stage 4, a 78% average reduction in the NOx emissions, and due to the reasons you'll be familiar with, but also then to understand the uncertainties within those categories as well, and also to be able to see the outliers. And so whereas most of these pieces of equipment were clearly compliant or within margins of error, we were also able to pick out where there were either potential compliance issues or where there was intersections between equipment and duty cycles that perhaps were not captured in the regulatory framework that were to flag to regulators potential areas of problem. So that sort of data came out of that work, and then we can also segment it in a different way, in this case, between the different types of equipment. And you could see, and it starts to pick out certain, problematic areas. So within the excavator group, even within stage 4, there was much higher average emissions than perhaps expected, and the trend over time was not in the downward direction. Now, clearly, even though we tested a lot of vehicles, there were sample size limits here, hence showing you the variabilities. But that's the sort of depth of the data and the ability to analyse that we have. Slightly easier to test were the generators on site, and putting up here three different pollutants from generators: NOx, particle mass, and CO2, and we're testing on the ISO 8178 cycle. We're able to see the relationship between the demand, the load on the engine, and the emissions for the different generator capacities. So I think the message is here not about any one specific result, but the ability to originate this sort of information in real world conditions. Second part of the construction, and just to broaden out from that one project, we were then, and we work extensively with the Centre for Low Emissions Construction, which is a centre of expertise in London that may be useful if you're not already discussing with them, to be in contact with them. It's part of Imperial College, a real centre of expertise on how to reduce emissions in construction. So there's not to go through the details in any particular depth, but in this case, testing retrofit technology here, and being certified by the Energy Saving Trust in the UK. And this was part of the construction of this, what's called HS2, which is a high-speed rail line cutting through the centre of the UK, which it's astonishing how much a meal the UK makes of building railroads, having pioneered it in the first place, but there we go. But there was, to the credit of the UK, there was a great deal of attention about how low emission all the construction around that rail system was. Then we also, with Punch Flybrid, we did analysis of an energy storage recovery system there, and also some low emission power generators with a particular innovative technology here from Aquafuel. So again, it's not so much the specifics of the particular technology, but the ability to go into the field and test something of almost whatever shape and size or innovative fuel, and being able to evaluate its benefit. And that's also where the database we developed comes in, because it does give us a very good, useful baseline reference point when we're trying to assess these new things. So that's the construction side. Moving on to marine, I should say, I mean, we don't, so the PEMS-based testing is not easily applicable to big marine. There we tend to confine ourselves to taking samples on, on tubes, or other sort of fixed collections, so we can then do laboratory analysis on it rather than real time. Having said that, we're able to practically do marine vessels up to this sort of size. So this is the Thames Clipper, which goes right through the centre of London, up and down, taking people between the West End and out to the O2 music venue in the east. And this is it's currently called the Uber, so Uber is currently sponsoring this. So we were asked to see whether switching to an alternative fuel would deliver significant, well, in this case an HVO diesel, would deliver significant CO2 savings. This was done last year, and it was involved a 59-mile route repeated over 4 hours, as you can see, cutting right through the centre of London. And the results were, again, we were able to demonstrate significant reduction in NOx emissions on a per kilowatt hour basis, and an even greater proportionate reduction in particle number emissions, and indeed a quite substantial reduction in fuel consumption. Because this was not just HVO, but interestingly, it was a combination of HVO with a hybridization system. Obviously, you would not have got that reduction on its own, but that was the nature that combined technology, and it was interesting for us particularly by bringing together hybridization with a renewable fuel. The second marine application we did was, again, coming back to the earlier days of the Industrial Revolution and how Britain pioneered it. I mean, in London, the Victorian drainage system in London was pioneering in its day, has turned into a real Achilles heel for the UK, because our drainage, our foul drainage system can't cope anymore with the population in London. So about 8 years ago, I think it was, maybe slightly longer, there was this big new project for creating the big new sewer for London. It's called Thames Tideway. More colloquially, it's called the super sewer, and it is a sewer, and it is big and great. So, and it actually runs almost exactly the same route as we were doing the Thames Clipper on the water surface. It actually runs along the embankment, and it is this vast east to west sewer. So you might ask, why are we involved in transporting effluent? Well, the reason is, in excavating this big sewer, the amount of spoil and earth moving that was required was enormous. And the environmental concern there was, how do we get rid of all this earth in the most environmentally friendly way? The default was to put it on trucks and just go and drive it somewhere, probably out to the docklands in East London, and dump it somewhere. But they wanted us to look at whether it was better in terms of CO2, fuel, and noxious emissions to put it on barges. And so, and use the Thames itself as the way of getting rid of it. And that's what these were the barges that we tested. In this case, they were dual engine barges, and we were able to PEMS test both engines separately. So these, I mean, obviously they were pulling big barges full of mountains of earth. And, you know, it's a really interesting, very challenging project, obviously with the wet conditions. But the key thing was, or the headline result from it was, actually, the barge does work in certain circumstances. The barge is the best solution if you're pulling a lot of stuff. So if you're pulling, hundreds of tons, and also if you are not pressed for time. So if you're happy to pull a lot very slowly through London, actually that is the best way of doing it. But if time becomes a pressure, or if the nature of the excavation means you've got more frequent lower amounts, actually it does not make sense to do it, particularly from a CO2 point of view, to do it by barge. And what happened midway through the project essentially was most of the truck fleets that were the default case upgraded from Euro 5 trucks to Euro 6 trucks. And Euro 6 trucks were substantially better, certainly in pollutant emissions, but they were also superior on fuel consumption as well. So the reference actually got harder for the barge midway through the project, which leads, I guess the headline conclusion is that, yes, barges can have a role within certain constraints, but they're certainly not a sort of panacea and a very simple, flexible solution. But setting aside whatever the specific conclusions are, that the ability to go into that sort of environment and assess those sorts of questions, in this case, which was not a regulatory question, it was a policy, environmental, sustainability, and also public engagement question as well. And last thing in the marine section is a completely not marine, but I didn't want to let you go without telling you also we can do trains as well. So ability to go into rail situations and test them either on load banks or actually in real world operation is quite possible and challenging but possible. So finally, alternative fuels. And I'm sort of sandwiching into my presentation actually a piece of work we did with the University of Oxford. In this case, it was tested on passenger cars, but that's irrelevant from the point of view of, in terms of the capability. And this was doing quite a simple test between E0 and E10 gasoline blends, which is far behind what the US is doing. But it was something that Europe agonized over for quite a long time. And what I specifically want to look at is not the effect on regulated emissions, but to use this to illustrate what we can do with regard to unregulated emissions, and that it is possible to test a wide variety of unregulated emissions in real world operations. So on a PEMS basis, not just on a lab basis. So those are as you well know, the pollutants that the current PEMS technology is standard. And I do realize obviously there's new things being developed for Euro 7 and you can put an FTIR on a vehicle, etc. But the specific things that we were interested in looking at were things like formaldehyde, acetaldehyde, benzaldehyde, toluene, those sorts of things. And not just exclusively those as well. We were interested in doing an untargeted analysis. So what is it there that we might not know is there, or that we haven't thought about might be a concern? And the point is, this is a generic as well. So this is not about finding out E10 specifically. It's as we push it up to higher than 10% ethanol, or we introduce other feedstocks into those renewable fuels, how can we come up with a generalized method for screening for new nasties or for quantifying specific unregulated pollutants of concern? So that's what this is about. And what I'll illustrate here is on the 6 passenger cars. This could equally be 6 pieces of construction equipment or on-road trucks or whatever. It's a totally generic setup based upon a standard sensors or could be Hariba, AVL, PEMS unit on a car, on a vehicle in the normal way. But then adding to that, we have developed a proprietary sampling system, which is a proportional dilution system, which samples off the flow tube and onto a bank of thermal desorption tubes and other absorptive materials, and crucially on a geofenced basis. So if you look carefully here, you've effectively got a matrix, a 4x4 matrix of tubes. So and you set up the test with up to 4 geofenced areas. So in the first part of it, it'll sample onto the 4 tubes, the first 4 tubes. The reason there are 4, by the way, is you have one set up for more volatile, one set up for less volatile, and you can have a molecular sieve for N2O, you can have a DNPH cartridge for formaldehyde. So you can choose what tubes you put in those 4 slots. But then crucially, once you get to the end of the first segment, let's call it the urban part of the driving, it will automatically flip at that geofence location to the second bank, which maybe is the rural section. And then again, we'll flip to the third bank, which could be a motorway section. Or you could have one as a cold start section. So you can flexibly set that up to, in a sense, this is compensating for the fact that it's not real time. It's pseudo-dynamic in that you can partition the data in that way. And then at the end of the test, you take all the tubes out and then you can subject it to, in our case, we have a 2-dimensional GC with time of flight mass spectrometer to do, in that case, we use that equipment so we can do this untargeted separation, identification, and quantification at very low concentrations. This does at least down to, it's very sensitive and selective down to parts per billion, if not lower. So if you're trying to pick out trace levels of particularly noxious chemicals in real world operation, this is the best way we believe to do it. That was the test route. I mean, in a sense, it's not particularly relevant except that there are 4 parts to it. Those are the 2 different fuels. So we got, rather than from the forecourt, we got specially blended to mimic, but in a known way. And here are the results, just to give you an idea. So this is to show what is possible. So you've got the E0 results on the left, E10 on the right. You've got the 4 different segments of the test, horizontally, cold start, urban, rural, motorway, 4 cars making up the 2 matrices. So immediately you're able to see, for formaldehyde, this is all formaldehyde, the dominance of cold start in the generation of formaldehyde, and the lowest being on the motorway. This is all on a distance-specific basis. On average, there's a 14% increase in formaldehyde on the combined cycle between those 2 fuels. Then we started looking at other aldehydes, and particularly acid aldehyde, and the precursors to those as well. This is just an illustration of how we're able, for all the different cars and duty cycles, relating the amount of alcohols in the exhaust to the aldehydes which were then formed. Equally, because we have that granular data underlying it, we can cut and dice and analyze the data in all sorts of different ways. What was striking in this case, and to some somewhat counterintuitive, is we did not see measurable formation of aldehyde emissions despite the addition of the ethanol to the fuel. What we did see, though, was precursors and other aldehydes in there. So we think the generalized notion that ethanol in gasoline leads definitely in all cases to acid aldehyde is not true. We also looked for other things. Acetone, for example. I picked this, it's a relatively common, but it's one which is essentially in certain concentrations, it's an irritant, but it also can lead to cognitive impairment, dizziness, that sort of thing. So again, it shows here, again, the dominance of the cold start part of it, that rural driving, so relatively high speed, but dynamic driving is quite high as well. But systemically between the 2 fuels, there was not a great deal of difference. Acetic acid, why is that? That's in very crude terms. Acetic acid is not good because it leads to acidification of the environment. Similar pattern seen, but we picked out here that car 1 had particularly high acetic acid emissions. But again, between the two fuels on the average level, there was no significant difference. Thinking more about other aldehydes and also toluene, and charted again here, and how those two things are potentially interlinked in their formation. We have charts here again with the toluene emissions on the horizontal and the benzaldehyde on the vertical. Again, cold start dominant, quite significant differences between the vehicles, but on average, no significant difference between the two fuels. So that's the sort of VOC side of it, and the final main unregulated, or in some cases soon to be regulated pollutant in real world conditions is nitrous oxide. And this requires a molecular sieve rather than a thermal desorption tube. Again, we've seen cold start N2O emissions about 8 times higher, irrespective of which of the fuels compared to the average. Rural, again, relatively high due to that dynamicity. But again, no systemic impact, no generalized difference between whether it's E10 or E0. And I realize, there are other technologies which have been introduced to measure N2O in real world conditions, and which are absolutely valid. But what we're getting here is N2O along with all the other things. And actually, we're able to separate and identify, I think, something around 150 to 200 species of VOCs in this test. So if I went back to the raw data here, there's a long list of other pollutants we've identified. So if your question is the other way around, is, can we see compound X in real world operation? That's where the untargeted analysis comes in. So those are the 3 areas. So construction, marine, a bit of rail, and alternative fuels. And what I'd like to message to leave you with is that we've developed and we've taken real world testing and tried to push the boundaries of it and try to bring to real world testing stuff that has often been the preserve of the lab due to the challenges of it. So here we've demonstrated that real world testing enables us to look at a wide range of pollutants, whether regulated or unregulated. Physically, logistically, quite a lot of this is quite challenging, but we've shown it's possible, and I confess that there's part of me that likes challenging, pushing the boundaries of what is possible and being able to test things that may not have previously been easily testable. We do official testing, as mentioned, the official, the ISM, that sort of part, but it's so much more than that as well. It's about the R&D, it's about looking what are the new emerging pollutants of concern. So it's not just about turning out what's required by the law today. Not least, and that applies to the fuel side, and being able to see what the real world effects are. We can also, as an aside, do exactly the same 2D GC to the original fuel itself and link the relationship between what's chemically in the fuel to what comes out of the tailpipe as well. So that's very happy to talk about that separately as well. Retrofit accreditation, we can do that as well. That tends to be within the idea of, what are the quick, cost-effective ways of emissions reduction? Regulation development is a long and hard process, but there are these quicker wins as well, which often need, being able to test lots of retrofits on stage 3 diggers in a quick space of time to clean up a particular urban air quality problem, for example. And ultimately, what it all boils down to for us, and what's really important for us at emissions analytics is, as I said yesterday, this is not just about ticking the boxes and being compliant. It is about actually reducing the emissions in real world conditions, because that's what it's really about. And by doing that, and the off-road sector has been so much more successful at that than the passenger car segment, as we well know, and long may that be the case, but it requires a surveillance and an awareness and a constant questioning of what's going on, and are all these new technologies that we've heard about over the last couple of days, are there any hidden downsides? Are there things we need to worry about? Are there potential other upsides that we're not focusing on yet that we can drill into? So it's thinking beyond just the narrow confines of what we have to do, and what else can we find out and be conscious of to make sure we ultimately do the right thing. So that's, thank you for listening and indulging me on that. And I'll stop there and take any questions if there are any before I close everything off. But anyway, thank you very much for listening.
I've actually got a quick question, Nick. You mentioned ISM quite a bit there. In Europe, we have stage 5 ISM. I'm just thinking about what is the timeline to see public results from that in the European Union? And do you think it's actually going to show that the real world performance of stage 5 is actually significantly better than stage 4?
I don't know on the timing. I would have to defer to James on the exact timing. But in terms of what I would say it's fair to say that in the most part, stage 5 is looking very promising. I think we identified at stage 4 certain problem areas, but stage 5 seems to be a much better work through regulation. I wouldn't go so far as to say it's a complete clean bill of health, but in terms of, we're not picking up any sort of systemic problems, just the usual cases here and there. In a sense, you do want to always be picking up the odd case here and there to know that your system is working. If you're never picking up anything, then maybe the system is too easy, or there's something wrong with your system. But I'm not flagging any major red flags at this stage.
Do we have a Danan?
We can do that. We do that. In that case, we didn't, but it's equally possible to sample pre and post CAT engine out, and would be very suitable for that sort of thing. Actually, in some of the explanations of those results, and perhaps the absence of acetaldehyde was because of the action of the after-treatment system and being particularly effective. So that's absolutely an experiment we can do using this technology.
Thanks. Any more? Yeah, Beth.
So just a question on maybe the diversity of engine OEMs that kind of appear in your non-road testing, specifically, how you're drawing some of the conclusions that you are, because there's different recipes that are used, across different OEMs in order to meet the emissions regulations, and I'm just kind of wondering, as you've done your non-road equipment testing, how much diversity do you have yet in terms of OEM diversity, and therefore the potential diversity in engine solutions?
Sure. So I would draw a distinction between the sort of ISM type work that we would do, which would be to a client request, which is obviously then a self-selecting group, and the wider programs that we run where we source the vehicle. And probably the images I showed didn't emphasize the diversity of equipment manufacturers that we did in fact test. It was unintentionally representative, overrepresentative some. I suppose with that database that we've built, that is not intended to draw any specific conclusions. It is to build a picture that then other people use for their own purposes. So that data is then made available. So people want to do benchmarking or whatever it is, or an independent objective view on performance. Now, obviously, you'd have seen on the charts that you not just had the mean figures, but you also saw the distribution and the sort of data, the number of data points. So what we adopt is essentially complete transparency around it. So these are the ones we've tested. These are the results. You can drill down to the raw data. There is a degree to which, and I guess put it very simply, we go and test what we can get access to. And that doesn't necessarily represent perfectly the population of machines out there. Some manufacturers are keener than others to allow us anywhere near their machines, I should say. And sometimes it's just, fortuitous as to, who were the contractors on the site at Battersea Power Station. So I'm not claiming that the population of machines in our database is a perfectly representative sample. What I would claim is that there is a spread, and it's transparent. And we're always seeking to add to it. And if there's any gaps in it, I'm very happy to swing into action and try and plug those gaps.
Thanks. Any more? If not, we'll let Nick wrap up, I think.
Great. Thank you. Thank you very much. So yes.